Hi guys, Mr. Kane here. Good to see you.
Hi, Mrs. Goswish here. Mr. Kane, what's on your board now?
Oh, that's a picture of me in a fictional place I like to call home.
Home?
Home. Home on the range?
Auntie M, where is home?
There's no place like home.
Yes, I wouldn't know. We're always here.
Hey, it's all good. At least we got good chemistry.
Yep, there you go.
So we're starting out here, guys, with Unit 4. Unit 4 is about the periodic table. It's kind of a brief chapter, so only about a week here. We want you guys to understand the history of and the organization of the periodic table. According to John Newland, Dmitri Mendeleev, and a guy by the name of Moseley.
So these three guys are the main characters, right? Because there are other secondary characters with the periodic table, but these guys are the main ones you got to know. Correct, Mr. Kane?
There's other characters like Ernie and Bert.
Yeah. Big Bird.
Yeah,
Okay.
well, all those guys, yeah.
All right. Explain why elements in a group have the similar chemical and physical properties.
So there's actually a reason for that.
Define the term periodic trend. And know and identify the names and characteristics of each group / family / family. We kind of interchange the name group and family, so don't panic. It is the same thing. So
Patterns and properties. It turns out that the periodic table is a tool for organizing properties. It's kind of like a supermarket. The supermarket has a bunch of aisles in it to help organize where things are inside of it. For instance, if I was going to go try and buy some cheese, I would definitely not walk down the cracker aisle.
or the bread aisle. True.
Exactly. I'd walk down the dairy aisle instead. The periodic table is meant for organizing the properties of the elements, and elements can share different properties. Things like the phase of matter that they're in.
Color. Reactivity. Ooh, I love the reactivity, especially with that group 1A.
Yeah, and you know what? Each group has a different reactivity with different elements. So some are reactive with oxygen in a certain way. Some are reactive with chlorine in a certain way.
Yeah. Salts.
They can form salts. And how many valence electrons they actually have. We haven't talked about valence electrons yet, but we'll get there.
We're gonna.
And et cetera, et cetera. There are probably dozens of things that we could pull out. But in regular chemistry, will we pull out dozens?
Have we talked about etc. yet, Mr. Kane?
Etc. Isn't that a Latin word? Meaning there's a lot more here, but you have to get a doctorate degree?
Yep.
Yeah, I think that's the meaning.
Ooh, Mr. Newlands.
Mr. Newland. Oh, hey, check it out. It's an English chemist.
Oh, another one.
Does that mean he teaches English?
Yes.
All right, so it's about 1860. The Civil War is breaking out in America.
Yeah.
And meanwhile, this guy, John Newlands, has nothing to do in Britain, so he decides to try and arrange the 60 known elements.
There were only 60?
Well, there were still 114 elements, but they only knew about 60.
Okay.
And there's a difference between how many there are and...
How many are actually on the table?
Right. And there wasn't a table yet, so there were none on the
Yeah.
table. So John actually gets credit the first organization. So he places these elements in his own table. He arranges the elements by property and by mass, and he notes that properties are repeated every 8 elements.
Okay. So the 9th element would be a different property from 1 through 8? Is that what that means?
Yeah, it would actually have a similar property to element number 1. So it'd have different properties than all of those elements you just listed. It would be repeat. And he arranged it so that elements in the same row. Now, guys, you got to remember there are columns and rows. So columns go up and down, and rows
Go across.
go across. So his elements were all similar in the rows.
And
across.
rows are horizontal. Okay.
Rows are horizontal.
Yeah.
So this is the law of octaves. Basically, what you're seeing here is you're seeing 8 elements that have similar properties
And characteristics.
and
So
characteristics.
he set it up with the groups going across the table. Okay.
Right, which is not how the modern periodic table is established, but
Okay. Ooh, he's scary looking, Mr. Kane.
he's that's a good looking picture. I like his whiskers.
Mm-hmm. He's a little scary looking.
Just a wee bit.
Dmitri Mendeleev.
All right, so Dmitri Mendeleev. Does it matter which part of Russia you're from? How you say
Yeah,
it?
Mendeleev. Now, if I remember a story right, him and another guy working on the periodic table, he got to the printers first, and I can't remember the other guy's name. Do you remember his name?
No, but I remember the other guy was in Britain.
Yeah.
So the Russian chemist takes tops on this
Yep,
one, right?
he got that one.
Okay. But Mendeleev's contributions, basically he bases all of his work on Newland's research, And he gets credit for the first orderly arrangement. So we actually call this a periodic table.
Okay.
Newland's was not periodic. Guess what? There's 3 more elements now that are known. So between the time that Newland did his research and Mendeleev was true in his work, found 3 more. Okay, so he also does things by atomic mass as well as properties, and he uses the symbols. He's just coming up with a different arrangement. What Mendeleev did that Newland didn't is he left gaps.
All right, so...
And he actually made predictions where those gaps were.
He expected some element to be discovered later and put in those spots.
Exactly.
All right.
Okay. So this is Mendeleev's first attempt. If you take a careful look at the table, you can probably try and see and figure things out. If you look here, you can see that lithium, sodium, potassium, rubidium, cesium, these are all elements that we know are all in the first group of the periodic table today.
Okay.
And they're all in the same horizontal row, just like Newland's might have set up.
So he went across also. He put his families across also.
His initial attempt was putting his families across.
Just above that one, I see the halides, the fluorine, the chlorine, the bromine, and the iodine.
Right. There we go.
Right. And I see a bunch of question marks, Mr. Kane. What are the question marks?
Here's a question mark here. Here's a question mark here. There's another one somewhere. I know there's 3. Oh, here's one.
Yep.
Here's one here. So there are several question marks on here. What these question marks are is where he was actually predicting that there should be an element. He realized between aluminum here and this element UR, which we don't have a symbol UR today, so I don't know what element that is, but he realized that some element was supposed to be in between, and he actually predicted that it should have a mass of 68. Okay, same thing happened here between silicon and tin. He predicted that there should be some element in between with a mass of 70, which that's actually important work there.
And these are all listed by a mass, not atomic number, correct?
Right, because we haven't discovered atomic number yet.
All right, okay.
In order to have an atomic number, you have to know the number of protons.
Which we did last unit. Okay.
Who discovered the proton now?
The proton was discovered by Mr. Rutherford.
Yeah, I think it was Rutherford, and
with
he
the
did
gold
his work.
Foil.
It was well after 1869, so Dmitri couldn't have used
Yeah.
that. Oh, by the way, guys, if you haven't paid attention yet, read the title.
Hey, extra credit. No, I'm kidding. No extra credit.
Okay, so in 1871, 2 years later, Mendeleev decided to take another attempt at this. He decided his first attempt that was mimicking Newland's wasn't good enough. So what he did was he actually, if you read the Russian here, this says group 1. So he made up a group 1, which has hydrogen, lithium, sodium, potassium, and so on and so forth down it. If you look at our modern periodic table, you'll see some similarities there.
So now he's going down.
Right, now he's actually going down. So he switched it up. Instead of going across, his families now are going up and down, which is how we have our periodic table structured today.
Okay.
Okay, and notice here he's got some idea here. This element and oxygen. Okay, so there's a how many of this element plus oxygen that it takes so that this is the reactivity with oxygen.
Okay.
Here, this group only takes 1 of the element plus 1 oxygen. This group needs 2 of the element plus 3 oxygens in order to form a compound. And here we've got some compounds with hydrogen. Apparently he didn't know about, or they don't form compounds with hydrogen. Okay, but that's interesting stuff, and that'll come in useful in the activity in class. Notice again here, guys, he's got a couple elements where he doesn't know the name of it yet, but he predicts the mass.
Okay, so for future.
For future. And well, we'll get into that.
All right, Mendeleev's table organizes in groups and periods.
Okay, groups being which direction?
Groups are up and down.
Okay,
Families,
so
up and down.
and down, and periods being?
Across.
Across, okay. Groups are family. Oh, there we go.
There you go.
Groups and families are vertical, and they share properties.
Okay. Periods are horizontal and increase by mass.
As you read to the right.
1871 left space for unknown elements,
which we were just mentioning. Those are the ones we just circled.
Yeah.
And he called them Eka something. So he, the one that was next to silicon, he called Eka silicon. The one that was next to, I don't remember what the elements are, but he called them Eka something. Eka in Russian means close to.
Okay.
The really neat thing for Mendeleev is that only 15 years later, he was still alive. those 3 elements were discovered.
Oh.
And the properties that he predicted that they would have
came true?
Were correct.
Oh, that's neat.
How useful of a tool is this table that is periodic that Mendeleev created? It's extremely useful. So his predictions about the elements were right.
Periodic law overtakes the law of octaves. The table is periodical.
Yeah, it's something that happens every once in a while, right?
Yeah.
Kind of like the ties that I wear on Thursdays. Yeah.
Today's table is based off of repeating trends and properties based on increasing atomic mass.
So that sounds like a definition.
Yep.
I wonder if that'll be important. It's a law.
Periodic law definition?
Yeah, maybe. Who knows? And this periodicity is known as periodic law. It kind of gets periodic. It almost repeats itself here.
Yeah.